Let's look at a complete example of a standalone Spark streaming application that takes place in the context of our killer video site. And this application is going to be really the minimum subset Spark streaming standalone program. It's got 6 steps in it. What we'll do is we'll import classes, make a configuration object, we'll initialize the streaming context and the Spark context, create the DStream object, define our computation, and then start it running and wait for it to terminate. We'll begin by importing these classes for Spark, Spark Streaming, and the Spark-Cassandra Connector. And we'll create a configuration object, we'll give our application a name, tell it where its master is located, and set just a couple of parameters. And now that configuration takes a little bit of explanation. The Spark-Cassandra connection host is the address of at least one node in your Cassandra cluster. Spark Cleaner TTL set to 3600 seconds is a thing we normally haven't had to think about in regular Spark applications, but this is the amount of time Spark will persist its computation metadata, the metadata that describes the directed acyclic graph. This is how long that stuff can live. Since a streaming application can be very long-lived, it's important to set this TTL to something finite. Otherwise, you'll have effectively a memory leak by constantly allocating new metadata and never throwing it out. Finally, setting the name of the jar or jars at the bottom there. Your app.jar would be the name of the jar that the build for this particular standalone program would create with the code that we're walking through here. Spark needs to know the name of that jar so it can distribute that code around the cluster. There are 2 ways to create a Spark streaming context. The first one relies on the configuration object we created up above and simply directly instantiates a new streaming context. The second creates a conventional Spark context first and instantiates a streaming context on top of that Spark context. Now you note both of them pass in a number of seconds. That number of seconds is 4. That's the batch interval. That's how long the receiver will wait and batch up data coming in off the input stream before creating a new RDD in the DStream. 4 is great for our illustration purposes here, and there really is no general purpose answer to what that number should be. That depends entirely upon the requirements of your application. If data is coming in at a very, very high rate, you're going to tend to want a small number to keep the data set manageable. If you have a requirement for processing latency that's very aggressive, like you need to make a decision within 2 seconds of some event on the stream, then you'd want to set that to a small number, like 1. In the absence of those considerations, you might be able to tolerate a larger number. The socket text stream method is creating the actual receiver. This is an API that creates a text receiver, and it opens a socket to that IP address and that port. It's going to make a TCP connection to that port and IP and expect to receive text from it. It'll create unique records in the DStream RDD by line feed delimiting the text that comes in. Since it's a text stream, that's the protocol it implements. Other kinds of receivers, of course, will do their thing, Twitter, ZeroMQ, Kafka, etc., but text stream works that way. Finally, we get to the actual computation. We've got our context created, we've got the stream coming in, we need to define what we're going to do with it. And it looks here like we are counting words. We're going to flat map those records, having delimited them on spaces. Then we'll count each word individually, which is really what we're doing with that map line. We're mapping word to a tuple of word and the number 1, because every time we see a word, we have seen it once. And then we'll reduce those by key, using the anonymous argument syntax in Scala there. That's going to give us, effectively, a pair RDD as output with the values of the key value pairs being the counts of words. And that's going to update every 4 seconds. We'll get a new one out of the computation every 4 seconds because we defined 4 as our batch interval. Finally, in our program, we'll start the context and we will await termination. Await termination will effectively block until the job is terminated. Now here is the complete application. Of course, you see in this code a little bit of naughtiness, like the Spark master and the Cassandra node things are hard-coded to the localhost IP address, and all that stuff should be passed in as parameters to the main method in a production application. But this program in its entirety could be compiled using SBT or Gradle or something like that. Then the jar that we get out of that could be submitted to the DSE cluster using the DSE Spark submit command and passing in the jar to it. That'll send it to the Spark cluster and allow us to run it. And here's some sample output. This is too long to fit on the screen, so we'll scroll through it. But every 4 seconds, we're going to get the output of the job. We'll see, for example, in that first output of batch data, we'll see 22 occurrences of drama, 12 of comedy, 16 of action, 9 of romance, and so forth. And if you look at the ending digits of that timestamp, there are 0, 0, 0, 0. And down below, we'll scroll down there. That's 4 seconds later. 4000 is the ending of that timestamp. But we have different word counts that happened during that stream interval. But you see that we have a running, standalone Spark streaming application, super easy to understand, something that you can begin with and extend for your own applications.